So kind of changing gears here a little bit, we also know that nuclear reactions produce a lot of energy, and that a lot of energy can be obtained from nuclear reactions. And so the energy for nuclear power plants come from obviously nuclear reactions. Nuclear weapons, when they go off, give off a lot of energy. So we're going to talk about that just a little bit. So you can actually do some mass energy calculations. We're not really going to get down into the details of this, but I'm just going to kind of superficially talk about it. But we know that when a nuclei of some force decays, it goes down in energy. That's kind of the whole purpose, is it's unstable, it gives off that energy, and it goes to a lower energy. So it's decreasing, it's giving off this energy. So that energy changed is related to changes in mass, according to E equals mc squared. So C is the speed of light, E is energy, and M, of course, is mass. So we can actually look at the change in, we can find the change in energy for a nuclear reaction by calculating the change in mass, the delta M. How in a nuclear reaction, how does the mass change? You can, and this is more complicated, and I'm just going to give you an example, but this won't be on the test, but the masses of some elements are given in the table, and you can actually add them up and see how they change over a reaction. So here's it's from a different book, but there's a table here of masses of some elements. You can see an electron. Here's the I'll get my pen out here. Here's the mass of an electron, very tiny. And notice that these are all out to many, many digits. The mass of a nucleus, a neutron, the mass of a proton. Notice a neutron is just slightly bigger than a proton. A hydrogen atom then that has one proton and one electron, you can add those together and we get a hydrogen atom. A deuterium, if you have one proton and one neutron, of course, will weigh 2. If you have tritium, which is hydrogen with one proton and 2 neutrons, and then you can see, so here's a helium atom, and these are some values that you can look up. All right, so just for example, let's calculate the energy change in joules for this following nuclear reaction. And in this reaction, we have deuterium, which is hydrogen with a neutron, helium that only has one neutron, so this is helium-3, which is a little bit light, and we're basically transferring a neutron from hydrogen to helium. And so we have helium-4 and then hydrogen-1, which is normal hydrogen. We can look up the values of the nuclear masses. These are what we looked up. The nuclear mass, though, is actually the mass of the atom, and we have to subtract the mass of electrons. So hydrogen has 1 electron, helium has 2 electrons. So we have to subtract that because we're using such significant figures, so many significant figures that we have to do this. So, so these numbers are actually the mass from the previous table minus, so hydrogen will be -1 electron, helium -2 electrons, and so forth. So we have these numbers, and then we can find the change in mass, and these are tiny, tiny numbers, but the delta M would be whatever the mass of the products, which are these, minus the mass of the reactants. I've already distributed the minus sign, so you could put minus the sum of those, but the negative's been distributed. And so in this case, the change in mass is negative 0.0190960 AMU. So this is the mass change for 1 mole of hydrogen 2. So it's equal to AMU is equal to grams, which is, you can convert that to kilograms. And then E equals mc squared. The reason why we converted that to kilograms is because the speed of light is meters per second, quantity squared, kilograms. And if you have kilograms times meters squared divided by seconds squared, that is equal to joules. So we're just doing some little finagling to get the units to be right, so to get in joules. So anyway, delta E equals that change in mass, in kilograms in this case, times the speed of light squared. And so you can see that it's given off, the change in energy, since it's negative, it's given off 1.76 times 10 to the 12th joules, or if you divide by 1,000, 1.76 times 10 to the 9th kilojoules. And of course, that's a 1.76 trillion kilojoules. That's a lot of energy. Like I said, we are not going to be doing any of these kind of calculations, but I just wanted to show you where some of that, how we can do that. Okay, so one of the processes is nuclear fission. Nuclear fission is a nuclear reaction in which a heavy nucleus splits into lighter nuclei. And when that happens, energy is released, and usually small particles are also released. So here's an example. Oftentimes this process just occurs spontaneously. So here's an example of californium fizzing, going under fission to create barium and molybdenum, and 4 neutrons are released. Notice that the numbers still have to equal. So, californium is a big molecule that breaks into smaller molecules, but notice that the total number of protons is equal. 56 plus 42 is 98, and then 142 plus 106 plus, notice that there's 4 neutrons, so plus 4 is 252. Oftentimes, you can create a nuclear fission by starting the reaction by bombarding the nuclear chemical with neutrons. So uranium, for example, can be induced to undergo fission by bombarding it with neutrons. Here's 3 different possible tracks. So if you bombard a neutron, take a neutron and it's not a simple thing. You got to get it moving really fast. But if you bombard uranium with a neutron, it can then break apart. It's not anything that you can predict, but it can break, for example, xenon and strontium with 4 neutrons, or barium and krypton with 3 neutrons, or cesium and rubidium. How it breaks is just how it feels at that moment. But again, notice that the numbers have to be. So if it breaks apart into xenon, then strontium is the other product, because 142 plus 90 plus 4 gives you 236. Don't forget to add this one here. I should use a different color here. If barium is one of the products, then krypton and 3 neutrons. So anyway, the numbers still have to add up. But what's happening, so what's important now is that these neutrons are being given off, right? So more neutrons are released, and so now you start a chain reaction. And so a chain reaction is just a self-sustaining series of nuclear fissions caused by the absorption of neutrons released from previous nuclear fissions. And so you also need to, in order to sustain the nuclear chain reaction, you have to have a critical mass, which makes sense. It's the smallest amount of fissionable materials required to get a chain reaction going. So the critical mass is just the minimum amount that you can get a chain reaction going. So here's kind of an example of a chain reaction. And so, we first bombard uranium with a neutron, and then the uranium breaks apart. In this case, it's barium and krypton, with 3 neutrons being given off. And if there's more uranium around, these bombard further and they break apart. again, barium, krypton, but then here we may have cesium and rubidium, xenon and strontium. Anyway, so we're giving off all kinds of neutrons, and so the chain reaction continues. So you might wonder, well, this is not a very pleasant topic, but when they dropped that first atomic bomb, how could they carry the bomb without it going off? Well, again, the if you have a mass of fissional material that is much larger than that critical mass, so it's called a supercritical mass, then it will cause a nuclear explosion. So if you have a supercritical mass, you will get a nuclear explosion. Well, how do you get it from not doing that at first? Well, so the atomic bomb was made where you had subcritical amounts of each of the fissionable isotope present, but they were separate from each other. So nothing would happen until you get you get the critical mass. And then you can see here, there's a chemical explosive. I mean, it could be just something simple, gasoline or something. I think it's a solid, but you get the idea. It's something that can be exploded easily, just a chemical explosion. Once that happens, then it pushes together these two pieces of subcritical uranium. Once they get together, now you're above the critical amount. You actually have a supercritical amount, and so the bomb explodes. In a power plant, nuclear fission is what produces the heat. And so there's a controlled chain reaction of nuclear fissions. And once that heat is produced, the heat is put into usually water, some kind of water that then produces steam, and the steam drives the electric generator, creating electricity. A nuclear reactor consists of fuel rods that have the fissionable material, and then also control rods which don't have the fissionable material. And in fact, a lot of times the control rods have ways to absorb some of the energy or the nuclear to try to control in case it gets out of hand. So one kind of nuclear reactor is called a light water, an ordinary water reactor, and those are common in the US. And in this case, the fuel rods will contain enriched uranium. So you've probably heard that in the news. What is enriched uranium? Well, uranium, you have different isotopes of uranium, and they're in a zirconium alloy too. But anyway, natural uranium, if you just were to mine uranium, only has about 0.7% uranium-235. So the one that you can cause to become fissionable. 99.3% of uranium is uranium-238, which you can't create a nuclear reaction with. It's probably radioactive, but you can't create a nuclear reaction with it. So if you want, so uranium enrichment is done by making the compound uranium hexafluoride, sending it into a gas centrifuge, and because 235 is lighter than 238, the 235 will stay closer to the center, the 238 stays farther away, and so you can separate them out by weight. So the uranium-235 becomes more concentrated, and then it does have enough to create a reaction. So reactor grade enriched uranium is between 2.5 and 3.5% of uranium-235, and if you're wanting weapons grade enriched uranium must be greater than 90% uranium-235. So you've probably heard that uranium enrichment usually having to do with nuclear weapons. Unfortunately, again, is not a very cheery topic. So even with this enrichment, it still takes about 3 kilograms of natural uranium to supply even with the necessity of enrichment, it still takes only about 3 kilograms of natural uranium to supply the energy needs of one American for a year. And so I think that's why nuclear energy is so popular. Of course, it can be very dangerous if not controlled. So, like I said, what's in a nuclear plant? You have these control rods. So, what are control rods? Control rods are cylinders that have substances that are able to absorb neutrons. So, they're able to kind of stop the collect the neutrons so that they don't hit more, stop the chain reaction. So boron and cadmium are something that don't mind. They can absorb these neutrons and slow the chain reaction. And so by changing the depth of the control rods, you can control how many neutrons are absorbed, and therefore you can control the chain reaction. If you drop them all the way down, they will stop the chain reaction. I watched the movie. It's kind of hard to watch, but Chernobyl, and it's interesting that the scientists who ran that didn't think it could ever blow up, and so, but there were all kinds of crazy things that happened, and so most nuclear power plants are perfectly safe. A moderator is a substance that slows down the neutrons that are produced from the reaction. And so they can be better absorbed by other uranium-235 nuclei to continue the chain reaction. So if you have fast neutrons, they're more likely to be absorbed by uranium-238. But if you want slow neutrons, you need if you want to react with uranium-235, you need slower reactions. So that's what the moderator does, is slows down the neutrons. And then the moderator for light water reactors is just water. So here's kind of a picture of it, a light water reactor. So you can see over here are here's the fuel rods that contain the nuclear material, and then we have our control rods. So they allow the chain reaction to continue if they're pulled up, but to stop the reaction, the control rods get pushed down, and so they can control the reaction that way. So then the energy comes out and creates the steam. The steam then can move the electrical generator. The water then is condensed back down into water that pumps through, and so it can continually come through. And you can see here that actually this water from the river or lake is actually cool water that is then taking the steam from the steam turbine and condensing it, and then that water circles through. Anyway, kind of interesting. There are other types of reactors. Heavy water reactors don't need the enriched uranium, but they do use deuterium instead of hydrogen in water. Sometimes you may have heard the word heavy water. And so, well, right here, heavy water. Heavy water is H2O, it's water, but instead of using the hydrogen 1 with with no neutrons, they use hydrogen 2, which has 1 proton and 1 neutron. So that's heavy because hydrogen is twice the mass of deuterium, is twice the mass of regular hydrogen. And so this heavy water actually can slow down the nuclei more efficiently, and so they don't need the enriched uranium. And then there's also something called a fast breeder reactors. And so they allow the fast neutrons to be absorbed by the uranium-238, which is not fissionable, and that creates isotopes of plutonium that are fissionable. And so this is a way of getting an even more more radioactive compound. Just to kind of complete the picture, nuclear fusion then is the opposite of fission. Fission breaks apart, fusion puts together. So nuclear fusion is a nuclear reaction in which light nuclei combine to give a more stable, heavy nucleus. And sometimes neutrons can also be released, and sometimes and energy is also released. So an example of nuclear fusion is this reaction we looked at. No, we didn't look at this earlier. But anyway, if you take deuterium, so hydrogen with 1 neutron, and tritium, which is hydrogen with 2 neutrons, and you force them to combine, and again, these have to happen at very high speeds, but if you force them to combine or at high energies, high temperatures, then they can create helium and a neutron. This actually, they've been observed in the laboratory using particle accelerators. Like I said, they have to be going really, really fast, otherwise they'll just bounce off each other. So to have a sustainable fusion reaction, you have to have temperatures of at least 100 million centigrade. At these temperatures, all molecules will dissociate into atoms, and the atoms ionize, forming a plasma, which is kind of the fourth state of matter. The principal source of energy in the sun is this net fusion reaction where 4 hydrogen nuclei fuse to produce 1 helium nucleus and 2 positron particles. The net reaction is 4 hydrogen come together to form helium and 2 positron. The helium nucleus has a mass that's about 0.7, we talked about this earlier, 0.7% less than the 4 hydrogens, and so it's this loss of mass that is converted to energy, and that is what sustains the fusion reaction. Hydrogen bombs are also nuclear fusion bombs. So the atom bomb was a fission bomb, but the hydrogen bombs are fusion bombs. In order to get the high temperatures necessary to get fusion going, you have to have a small fission bomb first ignited, and then the fusion reaction occurs. So that's kind of the end of this chapter. What should you be able to do? Remember, we're not going to do any of the conversion, the delta E equals mc squared conversions, but you should know what the nuclear symbols are, or be able to write the symbols for positron, gamma, electron, neutron, proton, and then any normal nuclide, so be able to write the nuclide symbols. Be able to write an alpha or beta nuclear equation from scratch if you're told that it's going to, something decays by alpha or beta, be able to write those. Be able to deduce the product or reactant in a nuclear equation. In other words, be able to, if there's one blank, be able to determine what goes in that blank. Be able to explain the band of stability and then predict the relative stabilities of nuclides. Will a particular nuclide be stable or unstable? List the 6 types of radioactive decay. Predict the type of radioactive decay a particular nuclide will undergo, like we did earlier in this this lecture. Be able to calculate a decay constant from the half-life, or be able to calculate the half-life from a decay constant, and then determine the fraction of nuclei remaining after a specified time. So using the first order rate law to be able to find the fraction of nuclei remaining. And then just in general, be able to explain why radioactive isotopes are useful and different ways that they are used. And that's the end of this chapter and the end of the semester.